Alrighty, how do you want to answer this first question here? Oxygen, nitrogen. Okay, so first off, nitrogen is bigger. All right, so there's two reasons why the nitrogen is bigger. How about answering why the oxygen is smaller? Okay, so that's not the answer. It's closer to fluorine. Actually, doesn't answer any question that I had just asked. So forget about that.
Forget me.
Okay, so number one, the oxygen. So this is why oxygen is smaller. The oxygen has one more proton. Therefore, it's pulling in harder. We good with that? It's only half of the question though, because if I move from, say, neon to sodium, that's not the case. I did go up a proton, but the atom actually gets larger when I move to sodium. So how do we...
Where is that in the row, right?
Same row? I don't care about the table. What do you... What does? You're going the wrong way. So even though the oxygen has one more electron, tell me about it. I know. We already said that. You're trying to tell me why it's closer to the nucleus. I know it's closer to the nucleus than the oxygen because the oxygen's pulling harder, but that's only half of the question. Because that same situation happens with neon and sodium. Sodium is one proton larger, so it should be pulling harder, and it is, but the atom is still larger than the neon atom. What do you mean? Don't say row. Don't say row. More specific than what's one step below the energy level. Okay, so tell me about that sublevel. No, not about pulling power for that sublevel. Tell me about the electron and that sublevel.
Because there's more pairs.
No, it's not about pairs. I don't know what you mean by that. So let's start with this. 1s2, 2s2, 2p4, and 1s2, 2s2, 2p3. All right, those are the electron configurations. So this guy here, this has one more. I don't know what that's doing. Has one more electron, right? Tell me about that electron. No, or tightly bounded. What was it put into? Sublevel. What sublevel was it put into? Any old P? The 2p, right?
Yeah.
So nitrogen has electrons in the 2p. Is the p filled? It still can hold 3 more electrons, right? So when I move on to oxygen and it's got one more proton pulling harder, it's also got one more electron. Where does the electron get put? Are you trying to say orbital?
Yeah.
Okay. Where is that orbital? Where does that orbital exist? This isn't filled yet, right? It's still not filled. So when I put that electron in, I put it into the 2p sublevel. that eighth electron.
So it goes in the same place.
It goes in the same place. We okay with that? It's the same distance away, the location, but now the thing that's holding them all in is stronger. Does that make sense? So what I've done is I've placed the next electron into a partially filled sublevel. So that sublevel isn't any further away than the last electron was, and the thing that's holding it all together is pulling harder. So this is you have to have both of those things happen. So tell me why the neon and the sodium, that didn't work when I said the sodium has one more proton, but its atom is actually larger. It's putting it into I've completed that 2p, and now I have to add it to a new sublevel that was physically further away. The analogy is you're like trying to buy tickets for a sporting event, like a Blazers game or something like that, and you put in Ticketmaster best available seat. If everybody puts best available seat, how's the stadium going to fill up? The front row is going to fill up first, right? No matter what the price is, if everybody just pays and they say, I want best seat. And then after that's filled, then I put the next row, I fill the next row up. So what's happening here is I haven't filled up the second row yet. So that electron, that person at that game isn't any further away from the action than any other person, than the last person that just got added to the game. Okay, so how about the oxygen and sulfur? Which one of these guys is bigger?
Sulfur.
Sulfur is definitely bigger. All right, so the sulfur is bigger. All right, what's the explanation here?
The oxygen still has less electrons and the larger nucleus than the tighter.
Well, the sulfur has twice as many protons, right? So it's pulling twice as hard. But the electrons that its outer electrons are where? Specifically? On the 3p sublevel. Excellent. Okay, so the outer electrons for oxygen are in the 2p, and the outer electrons for my sulfur are in the 3p. So they are physically further away. So even though the sulfur is pulling harder, twice as hard as the oxygen is pulling, those guys are further away, and it doesn't matter. They can't pull, it's not going to pull it in closer than the second energy level because the first energy level's there. Okay. What's more likely to lose an electron, the magnesium or calcium? Okay, so calcium is. Why is that? There you go. Calcium, these electrons for the calcium are 4s2, and this is 3s2. I messed that up. All right. Oh, that's right. 3s2, and then the last electron here is 4s2. So this is one energy level further away from the nucleus. So if the further the electrons get from the nucleus, what happens to the ability of the nucleus to hold on to those? Less. So farther away. So the calcium is actually pulling a lot harder though, right? How many protons does calcium have? 20. And the magnesium only has 12, right? But since those electrons, those two electrons are considerably further away from the nucleus, those extra protons are not powerful enough to pull it in closer than those magnesiums. So then it's more likely for that calcium atom to lose its electrons. Okay, so who's more likely here? There's two ways to figure this one out. Chlorine wins, okay. Why? That's not good enough. Because if it was oxygen, then oxygen wins, and oxygen needs 2, and chlorine only needs 1. What's the way that you know? A quick and easy way to know. Chlorine is closer to fluorine, right? That's how you know that. But explain how you can look on a periodic table besides this and quickly quantify the difference between those. What number should you be looking for? Those numbers that Linus Pauling came up with are the electronegativity numbers. On your periodic table, they're the little green number near the upper right-hand corner of the block for that element, and it says 3.16 for the chlorine, and it says 3.0 for the nitrogen. So that's telling you the larger the number, the more likely that atom is going to be able to take electrons away from somebody else. So that's how you're going to know that. The reasoning with this is the chlorine only needs 1 more electron, right? Write out the electron configuration, noble gas configuration for iodine. Okay, so let's do the noble gas configuration first. So I got an I, colon, the last noble gas from iodine is krypton, Kr, and then after krypton we're looking at 5s2, 4d10, 5p5. So the full electron configuration, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p5. What I'm hoping that you do with this I'm hoping that you see the iodine right here, and then you basically chunk out the periodic table based off of the sublevels. So the first 2 electrons go here in the 1s, and I can fit 2 there. And I can fit 2 electrons here in the 2s. And then I can fit 6 electrons here in the 2p. And then 2 more in the 3s, and then 6 more in the 3p, and then 2 more in the 4s, and then 10 in the 3d, 6 in the 4p, 2 in the 5s, 10 in the 4D, and then I get to not the full P, so 5 more fit in my 5P. So that's how I want you to think about this. And using the periodic table tells you, it lets you know how we're orienting those, in what order. All right, so now we want to draw electron configurations for these guys. So let's, I don't know. Let's do this. All right, so my electron configuration or energy level diagram for nitrogen is going to be, I need a 1s, and I need a 2s, and I need a 2p, and 1, and 1, and 1, 2, 3. So 1 up, 1 down, 1 up, 1 down, up, up, up. How do I know that this is what I'm looking for? This has 7 electrons, nitrogen has 7 electrons, so I'm done with that. Anything else? If I'm in the second row in the P block area and I move 3 columns over, what should I find? I should find a nitrogen. So when I do that, I'm in the second row here. I'm in the P block, and I'm in column number 1, 2, 3, and there's my nitrogen right where I expected. All right, I need a totally different pen. That's fine. I'm sorry, what are we doing next? Is it molybdenum? Molybdenum. All right, so I need some space. One S, 2S, 2P, 3S, 3P, 4S, 3D, 4P, 5S, 4D. All right, so 1 orbital, 1 orbital, 1, 1, 1 orbital, 1, 2, 3 orbitals, 1, 2, 3 orbitals, 1, 2, 3 orbitals, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. Okay. So 1 up, 1 down, up, down, up, down, 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 up, down, up, down, 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 up, down, up, down, 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 up, down, down, down. All right, so this is where it gets a little tricky. If I go up and down, and then up, and up, that's all the electrons that I have for molybdenum. So I'm looking at 42 electrons have been used so far. But molybdenum is part of the exceptions rule. So what's the exception say? When do I get to take 1 from that previous S? When the 4D could be half full or could be full. So right now, if I took 1 electron from the 5S, I would half fill the 4D. So do that. So this electron here gets put up here, and my electron configuration does not have an electron in the 5S. So if I counted this up, I'd have 42 electrons, so I'm definitely talking about molybdenum. I can't use that other way to determine if it's in the right spot, though, correct? Because if I went to the if I went to the 4D line and moved over to the 5th slot, I wouldn't find molybdenum there. I'd find an element that you can't find on Earth here, technetium. Freak of nature, it doesn't really exist. All right, so let's do copper. Copper has the same kind of situation, right? Except it's going to be full. So here's copper's electron configuration. So the important thing to note is this absent electron down in the 4s. So this adds up to 29 electrons, which is what copper has. And so if I would have drawn this the way you would expect it, what we would see is a filled 4s and 9 electrons in the 3D. But again, when we're in that situation, the 3D grabs that electron from the last 4s and finishes off my D sublevel. So how many exceptions do we have? How many are possible? So everything below, the 3 atoms below chromium and the 3 below copper. So 6 total, because each of those situations I'm half full or I'm about to be full.